Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Hi, I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe, and also a friend to my co-host.
Yes, I am your curious co-host, Connie, and we are entering a new year. How do you feel about that, Moiya?
I mean, the years keep coming and they don't stop coming.
Back to the rules and you hit the ground running?
I hit something.
Yeah.
In some state.
I feel like for the upcoming year, I don't know what to expect yet. I just spent a long time trying to curate last year, so I'm still in planning mode in terms of what I'd like to do or have happen or look forward to this coming year. But I know one thing that I'm looking forward to this year, and that has to do with you, my friend. You have a book coming out this year.
Oh, I do. I do. Yeah, Bestie, I know we've talked about it before, but not on mic. You saying that you feel like you're still prepping a lot sounds very much like, you've been living the year of the snake, according to the Chinese zodiac.
Yes.
And that we are stepping into the year of the horse, the fire horse. And, whatever we've been working on and prepping is finally going to come out at, like, the book. What's up, Bestie?
Beyonce.
That's all you needed to say. Oh my God.
For some context,
Act 3 is gonna be so good
because the fire horse is like what everyone thinks is gonna be the thing, and then it's the completion of this cycle. It just kind of aligns there. Wow. Anyway, what else do we look forward to this year, Bestie?
Oh yes, I have a book. I will be starting a new podcast this year. I'll continue doing Pale Blue Pod, don't you worry. And it's I'm not going to be producing the podcast myself, so it'll be a lot, I think, less of a lift for me. But
Yay.
I'm very excited. It's going to be about art and culture and AI and how we need to, protect art and culture from the rampant misuse, overuse, over-reliance on AI. So be on the lookout for that.
Yes.
I don't know what it's going to be called yet. There are a couple names floating around, but you'll hear about it.
Yeah, still in the planning phases for the year. So keep an ear out for that, listeners.
Is there anything that you will be kind of like wary of? Anything you're going to be on the lookout for this year? Because am I the only weirdo who prepares like that?
I'm sure you're not the only weirdo who prepares like that. Shout out to the weirdos. But nothing comes to mind at the moment. I mean, the general environment that we're in is kind of like I'm wary, obviously. But like on a, I don't know, more individual or personal level, not quite. I'm hoping to just keep up a steady incline.
Nice. I'm excited, but a little wary of the consequences. To live in Mamdani's New York. Like, I'm so excited. I very happily voted for him. I hope that my rent gets freezed. I would ride those free buses every day. I hope that he has very strong security. And, I hope there's no, retaliation against the city.
Indeed.
But, enough earthbound stuff. This podcast specifically focuses on things outside of Earth so that we can feel a bit more comfortable or, a bit distracted from what's going on the surface. So
yes.
Let's talk about the universe.
Okay.
Specifically, coming off of last week's episode, The Last Things in the Universe, we are going to be talking about the first things in the universe today for the first episode of the year.
Yes.
I say first things in the universe. What do you think of, Bestie?
I kind of just see blackness, but muted stars for some reason, even though those shouldn't exist in this. But they're just pinpoints, pinpricks or whatever. It's emptiness, but trying to imagine some sort of dust, which is kind of I guess particles trying to. And then they're just different particles. Kind of individual.
Swirl of particles.
Yeah.
Are you picturing glitter?
Yeah.
Like glitter and blackness?
Yeah.
Yeah.
Yeah, that's kind of the thing. Mm-hmm.
Cool.
Yeah.
I mean, yeah, why not? Yeah, just imagine like a hot glitter soup, and you've basically got the beginning of the universe.
Okay.
Mm-hmm.
Interesting. Mm-hmm. I'll say that, I grew up reading the Genesis version of the beginning, and it's just an interesting, and I think it's just like leftover like religious fear of just like this sense of breaking something that I was taught, So I actually have often avoided this topic, so I don't know very much. And there are ways in which I think the two can coincide, or there's ways in which I can see overlap. One doesn't necessarily have to mean the other isn't true for me, but it's just like I don't know much, because it's so many more detailed things that, again, I think could fit within the same story, but sometimes those things, also end up in conflict. And I hate conflict, so I run away from it.
Yeah. And it's not like that's an easy conflict to mesh together, especially if you have like heard of one, but it's mostly memories, and if you haven't really been exposed to the other. I personally am not religious. I don't believe in a God. I know many devoutly religious scientists. I know a few. I'll say I know a few devoutly religious astronomers who believe in God, and I've tried to like understand how they put them together. And from what I can tell, they just don't stare at the connection point too hard.
Yeah. Okay, so I'm sounding familiar.
Or they just think of God as like the ultimate physicist.
Yeah. The shepherd of this action.
The scientist of this action. Fuck a shepherd.
Yeah.
No, like like the actual scientist who made this experiment and knows all of the physics, and all of the stuff in the book is from people who couldn't understand the physics.
Exactly.
So I think that is how people combine it.
Yeah.
I'm sorry if fuck a shepherd offended you.
No. Because, like,
I would.
Also, it's, like, in many ways representative, but then also that has changed over the millennia. So, like, there's just, like, different layers to it. It's fine.
Yeah.
At least it's not Christmas week, like.
You're right.
We're in the new year now, so, like, whew. Okay. Anyway.
I think when you start to learn about the beginning of the universe, and then like as you learn more, you can try and mesh these two stories in your mind how you want. But learning more about the beginning of the universe, I think, is nice when you start with a big picture and then zoom in.
Right.
So big picture, there are like, I don't know, seven different stages of the universe that lead up to where we are today.
Okay.
The universe starts with the primeval atom, and an imperceivably small space that's filled with all of the energy that the whole universe currently holds. It was all in that tiny space. Then we have the inflationary period, which I'm going to talk about later, where the universe expands up to a much larger size. You get the first particles, but like fundamental particles, not even atoms, that form still in the first like second after the Big Bang. The first nuclei don't form until the first few minutes after the Big Bang. And so that's where we start to see like matter is like 3 minutes after the Big Bang. So entire books have been written about the first 3 minutes that lead up to that first material. I did an episode about the first 3 minutes. I think it was like one of the first 5 episodes of Pale Blue Pod. It might have been episode 3. So that is like the busy time where so much stuff happened, and it's very physicsy, and it's
very fast.
Very fast, yeah. It was a busy time. So after the nuclei form, the universe is still like a hot dark soup. We don't see the first light from the universe, the cosmic microwave background, which we talked about last week.
We did.
Mm-hmm. Do you remember what it is?
The first light of the universe, like photons?
It is. I mean, we see it in the form of light. So yes, it is photons, but it is a signature, basically like a snapshot of where all of the material of the universe was at this specific moment. And it's the moment of recombination when all of the electrons bound on to those nuclei and became neutral atoms for the first time. So that happened much later. And then the stars came much after that. So we don't start seeing stars until a couple 100 million years after the Big Bang. And that is when I think most people start thinking about space. To them, space is stars, it's galaxies, and it's that stuff that we see when we look out at the night sky. None of that existed until hundreds of millions of years after the Big Bang.
So first light happening before first stars. Tell me what that means.
Stars are not the only objects that emit photons. Any energetic process can emit a photon. We've talked before about how when an electron moves to a lower energy shell in an atom, it will release a photon that matches the energy that it lost. Early on in the universe, there weren't stars, but there were still electrons in atoms, and they can move. And the first light is especially important. You needed to wait for the electrons to bind on to the atoms, because when the electrons are free floating, all of the photons that are formed and like still exist there, they are bouncing off the electrons too much to escape. Like the electrons trapped the photons in. So we can only start seeing the universe when the electrons let the photons escape.
Oh, okay.
And then the atoms that those electrons were now in, they can combine and fuse, which is what stars are. But you get light before you get stars.
Huh. Just interesting in terms of the Genesis story. And the first one is let there be light. And then there was light. And then he creates the sun and the moon. And then the night and, the day and the night were...
Oh, so it matches Genesis.
The first day. Yeah.
Oh, that's nice.
Yeah, yeah.
I like when they line up like that.
Yeah.
I mean, that's like the big picture view. You get those stages. So there's the atom, inflation, the first particles, the first nuclei, the first light, the first stars. And once you have stars, they can combine with each other. They can gravitationally influence each other and the gas around them.
Right.
And when they get enough in a group, when they form a little gang, they have a galaxy. A little ganglaxy.
A ganglaxy. That is the official now scientific term for a group of galaxies is a ganglaxy. Ganglaxy. Okay. I'm gonna write that one down.
Yeah. Move aside galaxy clusters. That's good. So those are the big picture items. Do you have any other questions about them aside from first light? And I will get into them in more detail.
No, that was great. Thank you.
Okay. Well, then let's start at the beginning. This is pre-inflation. This is like the universe in its kind of initial state. It is tiny and it is hot. The best estimates we have for the temperature are really just based on measuring the temperature of the universe now and also being able to measure the temperature of the universe at more distant times by looking at the cosmic microwave background and observing distant galaxies, because the farther away we look, the farther back in time we're looking. So we can measure like the temperature at these different times, and to go back to like that gives us a trend that we can follow, and then we can just follow that to go back to the beginning.
Apply the formula, basically.
Exactly, yeah. It's plug and play at that point. And so we estimate that the initial temperature of the universe was 10 to the 32nd power.
You did this to me last week, where there was just like numbers so big that like you can't even say them, because like they go above like the regular like what people know of as exponential numbers. Like we talked about Googleplexes last week, and I'm just like, hello? Here we go again.
Yeah, sometimes the numbers get so big that we just have to use the numbers. So that's the temperature, and the universe is also very tiny. It is 10 to the negative 27th power meters across. At this point, it is smaller than an atom, like definitely smaller than an atom. And it is so hot and energetic that all of the fundamental forces in the universe, the gravity, the weak nuclear force and strong nuclear force, and electromagnetism, they are all unified in a grand unified force. This is theoretical. This is according to the grand unified theory that was proposed in 1974 after scientists noticed that when you get high enough energies, and we can recreate these in particle accelerators, when you get high enough energies, forces that usually have different strengths and rule different domains, that they will work together and with the same strength in their whole grand unified force. I don't know what that means. Like all I could find was that the grand unified force, it dictates the behavior of fundamental particles in the early universe. And I still don't, like, what does that mean? What does that mean, scientific paper?
They're like, it's the Force from Star Wars, obviously. Because I'm like, it just works in sync, is what it sounds like they're saying. It's like, we don't know how, but they just all work together.
They all work together. And I guess, there aren't really different types of particles for them to work on. But yes, initially we believe, according to the grand unified theory, that they were unified at first. Yes, bestie.
Grandma, real quick. Hello. Okay, good. Thank you. Okay, have a good evening. Rest up, okay? Okay. Bye-bye.
Well, that was adorable. Tell your grandma I say hi. And also maybe tell her that very, very early on in the universe, gravity was the first of the 4 fundamental forces to split from the unified force.
Will do. First thing when I see her. Did you know?
Did you know? Okay, so now we have the after gravity splits, we have the strong, weak, and electromagnetic forces together. They continue to decouple as the universe gets cooler and less energetic. So the strong force splits off next, and then the electro-weak force splits apart. So now we have 4 fundamental forces. After gravity splits off and we just have those other 3 unified together, as far as I could tell, that is when we think the force-carrying particles like gluons and photons and the W and Z bosons, they form in that moment.
A gluon?
Yes, we have talked about this before. So there are different types of fundamental particles. There are matter particles and force-carrying particles. The photon is the particle that carries the electromagnetic force. The gluon is the particle that carries the strong nuclear force. Because it's like it glues particles together, and the strong nuclear force is what's responsible for like making fusion happen and getting these particles to overcome the natural repulsion of electromagnetism, because they have atoms with electrons on the outside of their shells, so they shouldn't be able to touch, but the strong nuclear force can overcome electromagnetism and get those particles to touch and fuse together. And so we've called it the gluon because we're like, it holds them.
Yeah.
Right. So the force-carrying particles, they form after gravity splits. And then we enter a new epoch, a new era of the universe, the inflationary epoch. This lasts a tiny fraction of a second. It starts at 10 to the minus 36 seconds.
What?
And yes. So the fraction is 1 over 1 followed by 36 zeros. And it goes until 1 over 10 to the 32nd power seconds. So we're talking about literally less than quadrillionths of a second.
Okay.
So it's just, if the numbers are hurting your head, you don't think about the numbers. Just think in a very small amount of time, faster than you could blink, faster than...
less than a microsecond.
Yeah, faster than any process you've ever experienced. The universe inflated. It grew up by 10 to the 26th power. So it went from being smaller than the size of an atom to being about the size of a grapefruit, which doesn't sound very big. But that's basically the same thing as taking, like, I don't know, like a blueberry and turning it into the solar system.
Yeah.
So really ballooned up in size. And this is when the universe is finally cool enough for some of the matter particles to come into existence.
Because everything's not all up and on each other. Everything's gets a little more room to do stuff.
Yeah, to do stuff, to breathe, to expand and take up some space. Yeah. So this is where we start seeing quarks, which are the like fundamental particle that makes up protons and neutrons. Remember, there are already the gluons, because they're one of the force-carrying particles, and now we have quarks that have formed. So at this point, the entire universe is a hot soup of what scientists call a quark-gluon plasma.
And it's still about the size of a grapefruit?
Still about the size of a grapefruit.
Okay.
So it's a grapefruit full of hot, molten material with electric charge that is like, and I say hot, I mean hot enough to literally melt protons and neutrons into their components.
Whoa.
So like the protons and neutrons don't exist yet, but if they did exist and we heated them up to this temperature, they would melt into quarks and gluons.
Okay, yeah.
Hi, friends. It's me. Connie went to the campus cafeteria to get some soup and a grapefruit. I guess our conversation inspired some cravings, and me too. So I figured I would take this time to share some messages with you. And as always, the first message is a thank you to all of the patrons who support Pale Blue Pod financially each month. Thank you so much. We are an independent show, so it would be really hard to make this show without your support. And I want to give a special shout out and a huge thank you to the sun-like stars in our Pale Blue Pod sky: Scott Reynolds, Tom T, Nicole Bartlett, Ashley Shambo, and Bruce Sedloff. Thank you, my golden friends. I'm so happy that I can look out in the sky and see you all shining each night. If you want to support this indie podcast on Patreon, you can hear your name on the show, make it onto the patron star chart, and get research notes for most episodes for $5 a month at patreon.com/palebluepod. You can also make a one-time donation and become a supernova in our Pale Blue Pod sky. You can do that at the PayPal link in the episode description if a monthly donation is not a thing for you. And of course, if you can't support Pale Blue Pod financially right now, I understand, and we love you because you're still space. The best way to help the show grow is actually to get more people listening to it. So take the link to this episode and send it to someone who's been interested in the early universe or interested in how the Big Bang happened or something like that. And that way you're helping the universe make a new friend. We will thank you in advance on the universe's behalf. My next message is a podcast recommendation. It's another show in the Multitude Collective, and it's called Wow If True. Wow If True is your one-stop internet culture shop explaining how what's happening online shapes the real world. The hosts are the internet experts and real-life besties to unravel it all. One is a tech culture journalist, Amanda Silberling, and the other is science fiction author / attorney Isabel J. Kim, Esquire. Most importantly, though, Wow If True is the only podcast that will mention Neopets and horizontal mergers in the same episode. I just listened to their episode on enshittification with Claire Aubin, who hosts another show on Multitude called This Guy Sucked. And together they were talking about why the internet sucks, kind of tracing the causes of, like, why is the internet different today than it was when I was growing up? So check out Wow If True wherever on the internet you get your podcasts. New episodes drop every other Wednesday. All right, Connie's back with the fixins. Ooh, cheddar broccoli. That's very exciting. All right, we're going to eat these snacks and then get back to talking about the first things in the universe.
After the inflationary epoch, we get the quark epoch because all of these quarks have started to form. This is from 10 to the negative 12th power seconds to 10 to the negative 6th power seconds. So we are finally at 1 millionth of a second.
Compared to last week, this is like going in BC, like in time. Last week we were kind of like going increase, like, okay, just going forward. And so the numbers just kept getting bigger. But now it's like when Julius Caesar ruled from 44 BC to like, 41 or whatever the years were. It's like, right, okay, you're going backwards to reach a kind of a zero-ish.
To reach one. To reach one, yeah.
To reach one.
Mm-hmm.
Yeah.
So we're going from 1 trillionth of a second to 1 millionth of a second. This is the quark epoch. Just no.
For 1 second, there's an epic.
For a millionth of a second.
You're right. I didn't know that we counted epics. Epic. I'm having an epic right now.
It's epoch. It's not EPIC. It's EPOCH.
Epoch.
It's an epoch. They can be tiny.
Okay, I didn't. Sure. Like, I guess because it is a significant age of the universe, it gets its own epoch. But like a millionth of a second?
You straight up said no. You just rejected it.
I don't mean to reject science.
You were like, not today, science Satan.
Right? Yeah, I don't mean to reject science. I truly don't. But that's just, it's just too small for my brain. This is why I didn't do chemistry and why I wasn't going to physics, because they were too small and too big for my brain. And biology was really where it sit, because I could see the lungs. But you're giving me time in a millionth of a second. And that's its own era.
Yeah.
Of the universe that is going to exist until 10 to the 100th power years?
At least. In the heat death scenario. I didn't even tell you about the big slurp, bestie. And I don't think I'm going to tell you about the big slurp until you're like 70.
Please, yes. Please don't tell me now. Whatever we end up doing in the middle of now to then, whenever we get to then, we have to be like, we finally did it. I'm finally going to tell Connie about the slurp. The great slurp?
The big slurp.
The big slurp. Oh, no. Okay. We're going to save that one for episode 10 to the millionth.
Yes. Fair enough. I'll start the countdown clock.
Okay, great.
Okay. Are you ready to hear about the quark epoch now?
Yeah.
So during this epoch, the universe has cooled down to the breezy temperature of 10 quadrillion degrees.
I did actually expect you to go exponents again, so it delighted me that it was just a regular word.
This is 10 to the 16th power degrees.
That still makes my head hurt, but quadrillion, it's a word. Great, I get that one.
Good.
Okay.
And this is where more elementary particles start to form. So now we have electrons and neutrinos and a lot of quarks and antiquarks. At this stage, we have what scientists call baryogenesis. So the genesis of baryons. And baryons are types of particles that are made up of quarks. Specifically, they have 3 quarks in them. So like protons and neutrons, they're each made up of 3 quarks. You can have another configuration of quarks where if it's just one quark and one anti-quark, then you have a meson.
Mm-hmm.
Particle physics is just like that, where there are like all of these very specific words for types of particles that you have. But for some reason, like the interesting thing here is that for some reason that we do not know, there were very, very slightly more quarks formed than antiquarks by a factor of like for every billion anti-quarks, there was 1,000,000,001 quarks.
Okay.
And so when you get the matter and the antimatter together, they annihilate, just like in the Hawking radiation we talked about last week.
Okay.
So here, all of those quark-antiquark pairs would have annihilated, except there was this weird asymmetry, this weird imbalance that meant there were ever so slightly more quarks. So now our universe has matter in it. This is the point.
So it's kind of like not necessarily an accident, but like it kind of just happened.
Kind of just happened.
Okay.
Yeah, and we don't know why. And so all of the matter that we talk about, the stars, the planets, you, me, that is called baryonic matter. It is made up of baryons, which means all of the particles in the atoms, the protons and neutrons, have 3 quarks. Dark matter is a type of matter that is, as far as we know, not baryonic, but about 5% of the entire universe is this baryonic matter, and it was produced at this age in the quark epoch during baryogenesis.
In a millionth of a second, at the size of a grapefruit.
Yes. Well, at this point, the universe has continued expanding, so maybe it's like the size of a mansion by now.
Okay.
Yeah. Okay, so that's the quark epoch. After that, from a millionth to a second to 1 second. So for basically almost an entire second, we have the hadron epoch.
It happened again just now. Happened again.
Yes. It happened. There it is. There it is.
There it is.
So the temperature here has finally cooled enough for quarks to combine into hadrons. Any combination of quarks is a hadron. So both baryons and mesons, they are both like subcategories of hadrons. So when we talk about the Large Hadron Collider, this is what they're colliding. They are colliding particles that are made up of types of quarks.
Okay.
Yes. At this time, you do see a lot of anti-hadron being formed. So the hadrons and the anti-hadrons, they will annihilate each other, but there are ever so slightly more hadrons because there are ever so slightly more quarks than antiquarks. But because all of these hadron pairs are annihilating each other, there's this new type of particle that is becoming more dominant called the lepton. A lepton is a class of particle that is fundamental in its own right. It's not made out of quarks. So like an electron or a muon. These are types of leptons. They start to dominate the matter. They're not baryonic matter because they are not made out of quarks, but they start to dominate the matter content of the universe because all of the quark stuff is annihilating with its anti-quark companions just for a little bit, just for like this 1 second.
Wow. Okay.
After that 1 second, now we start getting into the atoms and stuff. This is where nucleosynthesis starts. I don't know why they didn't call it nucleogenesis, but maybe because they aren't just being like formed from nothing. It's the combination of multiple things. But from about 3 minutes to about 17 minutes later, so from 3 to 20 minutes in the beginning of the universe, atomic nuclei start to form when protons and neutrons fuse through the strong nuclear force, and the gluon, the particle that carries the strong nuclear force, is constantly being passed back and forth between the protons and neutrons to like keep them there.
Okay.
Eventually, after those 20 minutes, the universe cools down to about 1 billion degrees. So the whole universe isn't as hot as the cores of stars. So you can't just have fusion like happening out in the air.
Because things are more farther apart now.
Things are farther apart and they're moving less quickly and they have less energy to overcome barriers.
So sometimes maybe just like grazing or bouncing off instead of colliding.
Yeah. Or just missing each other completely.
Yeah.
So that's for the first 20 minutes. Finally, we have nuclei. It takes another 300,000 years for the universe to cool down for recombination so that all of the electrons can join those nuclei and create atoms. 300,000 years. And still, that's the first light of the universe. Still, we don't have stars. Still, we don't have elements heavier than like lithium. So it takes another 200, 300 million years for stars to form and start fusing heavier elements in their cores to make iron for the first time.
This is such a hurry up and wait situation where it's just like this one part is like half a billionth of a second, and then it takes a billion years, and then half a billion of a second, then a billion years.
Well, it doesn't go back and forth like that. It's like, like this first thing takes 1/4,000th of a second, the next thing will take a millionth, the next thing will take a second, and then the next thing will take a billion years.
Oh.
It just gets longer and longer for these processes because they're getting more and more complicated.
Right. Which part, like, is there a specific part that is the bang, or is it the whole process?
The bang is the initial.
Okay.
Like,
okay.
You know, once the primeval atom is formed, that is the Big Bang. Like, I think people think of the Big Bang as the explosive outward motion.
That's... Okay.
The Big Bang is just the beginning. It's a terrible name for what actually happened. Inflation is not the first thing that happened in the universe, but that might be what people think about because it ballooned out. But it wasn't an explosion. No, it was just boys trying to come up with a cool name.
Yeah. But it's more just like rapid growth.
Rapid growth is one stage of it.
Right. Yeah. But it's not an explosion as in like force out.
Correct. Well, I mean, except dark energy.
Oh, yeah.
But it's not a combustion.
Right. That feels like what the name implies.
Yeah. Not combustion, not an explosion, but there is an expulsive force. I have here a list of different types of particles, mostly.
Okay.
I did... one of them is not at all a particle.
Okay.
Most of them have not been observed. I think maybe like one of them has been observed.
Okay.
And some of them are physicsy things, but not particles.
Okay.
So all you have to tell me as we go through this list of 9 is if you think it is a particle or not.
Okay.
You have a 50-50 chance, and we'll see how it goes.
Okay.
But I mostly just wanted you to see the names of these things.
Of course. Because, wow.
Yeah. Okay, so a parton. Did I make it up?
I really
Or is
was
it a
like...
particle?
Right. I was like, did you make this up? And it's a dolly type of particle. I'm going to guess no, not a particle.
It is a particle.
Okay. Is it named after Miss Dolly?
No. It's actually so stupid. So a parton is a class of particle that describes what can be within a particle that resides within a nucleus. So it's like the fundamental particles that combine to make atomic nuclei. So it's really just like quarks and gluons.
Okay.
And that is a class of atoms that, you know, this one scientist, I think it may have been Enrico Fermi, who was apparently referencing these particles enough that he needed a word for them. So he was like, these are the particles that are a part of bigger particles, so they are partons.
Partons. I guess. And it works with the other names because they all kind of end this way.
They all end this way. Yeah. An axion, bestie.
Not a particle. Isn't it like a... Oh, no. Is that an axiom? Like there's a phrase, like a part of... A type of speech
that
I
that's
think
an
I was
axiom.
thinking of. Yeah, axiom. Okay.
I thought you were thinking about the namesake of axion, which is a cleaning agent from South America.
Ajax? No, not Ajax.
Not Ajax, but yes, a cleaning agent like Ajax. No, it was called axion from South America. And this is a particle that is like a hypothetical particle that could be what dark matter is made of. It was proposed in the 70s, I think. It's a particle that would be produced every time this like weird rule of physics is broken. This weird rule that has to do with the weak nuclear force and should be broken fairly often. But the problem that this convenient solution solved was called the CP problem, which stood for charge parity problem. But still, the fact that the CP problem was fixed with a particle named after a type of soap has always sat with me some type of way. Because we could have called it the Higlet.
That's funny.
And that's
That would be cute.
fun.
That would be cute.
So yeah, it was a particle.
Okay. Then I don't know if I'm going to get... I feel like but there's one that I think I do know. I think.
I'm excited. Gnomon.
You know, I'm going to guess no because it's been 2 yeses so far.
Yes, you're using the like the test trickery.
Oh yeah, the B. This one's got to be C.
You're correct, bestie.
Yeah. Gnome, but I wouldn't be surprised if they named it that. So that's why I'm like, who could tell?
The gnomon or the gnomon is the part of a sundial that stands up and actually casts the shadow that tells you what time it is.
Is that where we get gnome from? Like maybe like garden gnome?
Oh.
If the name goes back that far, but I don't know that gnomes aren't really Greek, or sundial's not specifically Greek.
Sundials are Egyptian.
Okay.
What an interesting question. I don't know. But, you know, just like we have decided that Johann Ritter, discoverer of ultraviolet rays, was the great-great-great-grandfather of John Ritter, I think we can decide that gnomes etymologically come from sundials.
Yeah, because that's why you put them on your lawn in the sun.
Yes, because you're hoping that they will cast a shadow on
and tell you what time it was.
Yes, I was trying to go even woohooier. They'll cast a shadow, you know, on any doubts or aspersions that people are casting your way.
Right. Yes. Yes. Absolutely. No man.
Okay. Yes. Let's move on. Okay. Then let's go on to Geon. Is this a particle or not?
No.
Yes, you are correct. But it's a little tricky because a geon is a single gravitational wave. It's like a protrusion in the fabric of space-time. Not the whole wave, not many troughs and peaks, but just like a single thing. And if a particle in quantum field theory can be seen as a spiky standing wave in a quantum energy field, then is a single gravitational wave not basically a gravitational particle?
Is it not one of, what is it? It's not welcoming among God's creatures. Like there's some meme that goes around. But yeah, it's like like it's a water droplet, but then there's a cup of water, and then there's the ocean. Like it's a piece in like sand, like a piece of sand.
Yeah, a piece of the whole.
Yeah, and then there's like a sand wave that can, you know, come at you if you're in 1999's The Mummy.
Yes.
Okay.
So it's not a particle, but I feel like there are some debate stages where if you're talented enough, you could convince people that it should be counted as a particle.
I see that.
Okay, what about chronon? Or chronon? You say yes?
I'm going to say yes. Just
because.
50-50.
Yeah. No.
Okay.
This is conceived as the individual unit of time. So in most conceptions of time is continuous. So you can't split it up into discrete quanta. You can't split it up into discrete quantized states. Whereas like a light wave, you can split it up into individual photons. A wave of water, you can split it up into individual, not just water droplets, but individual water molecules, right?
Yeah.
Time, if it is discrete, will have individual units that you can break it down into. And that is, hypothetically, what a chronon is.
And you don't mean as in sequential, because like in terms of like a second or a minute, it's more like
like inherently, yes, almost like a time comes in packets. Like a movie feels continuous, but it's many pictures. And so a chronon would be like an individual picture shot in a movie.
Okay. Like film, specifically, not like the pixels in digital.
Yes, yeah.
Okay.
Yeah, like when you get a string of film, a chronon would be like one of those little snippets. Yeah.
Okay.
But this is just like theoretical. What about a tachyon?
I'm going to say yes, and that because I see the next one is bradion, and I know that tachy is fast, and brady-ish, maybe, or because bradycardia is slow. Oh. And so I'm going to guess that they're both particles. One goes fast, one goes slow.
Yes, bestie! I'm so happy.
And that's why I love words and suffixes and prefixes.
Oh, I'm so excited. Yes, a tachyon is a theoretical particle that always moves faster than the speed of light. So it's going fast. And that's completely hypothetical. Like we've never observed one. A bradion is a particle that moves slower than the speed of light. So like every particle that's not a photon. I didn't know that Brady was a prefix for slow. That's so exciting. Makes me love Tom Brady's name so much.
Never thought about that. I haven't seen anyone make that reference. I just have anxiety, so I've looked at my heart a lot.
Oh.
It's like, do I have tachycardia? Okay, the opposite is bradycardia. Great, thank you.
Another word for bradyons is tardions. Like they're always tardy because they're slow.
They're tardy to the party of space.
Yes.
They're just moseying their way, lights just passing them by, just zooming on the highway of space, and they're just like, just making my way downtown. Yeah, they're not actually making their way downtown walking fast. They're slow. So both of these are theoretical, or one
tachyons are theoretical. Everything else that's not a photon is a bradion.
Right, because that is slower than light. Yeah.
And finally, we have the graviton. Particle or not?
Wait. And I'm pausing because I think, a geon is the one that's like an individual grain, so to speak, of gravity. So a graviton, I'm going to say no.
It is.
So you're trying to trick
a particle.
Me. Okay.
I'm not. It is a theoretical particle, the force-carrying particle for the force of gravity. So the reason people treat gravity different from the other fundamental forces is that we don't really know how it works outside of Einstein's relativity description that says it's like a consequence of the shape of space-time. Whereas the other forces, they're inherent. They're not a consequence of things. They are, like capital A. And also, the other forces, we've observed particles that carry them. Like we see the photon. We see the W and Z bosons in these particle accelerators. We have never discovered or observed a particle that carries the force of gravity. So we don't know if it exists. But if it did, we would call it the graviton.
Okay. That makes sense.
Honorable mention, because it didn't make the list because I just remembered it existed, is the inflaton, which is the particle that is hypothetically responsible for inflating the universe in the inflationary epoch. Oh,
go figure.
Yeah, that was it. Those are some particle names.
Those are fun. That was fun.
That was fun.
It was just my quiet voice. Just my quiet voice. Like, that was fun. I learned so much.
Yeah, particle physics was one of my favorite things to study for on the physics GRE because Hank Green has a song that's really fun about it.
I can't believe quarks are up, down, charm, strange, top and bottom. Like that just, it's real creative over there, it sounds like.
Sometimes,
yeah.
Particle physics is weird. It's just like filling in this grid of particles that we expect to find, and we're trying to keep symmetry rules in place. And I would never want to do the science, but I do occasionally enjoy hearing about it.
Right. Is particle physics and theoretical physics the same thing? Or
Not
is
the
it
same
just
thing,
overlap?
but related.
Okay. Because I feel like last week was a lot of theoretical physics and this week was a lot of particle physics, but I wasn't sure if that was like an actual separation or not.
Yeah, distinct, but yeah, there's a Venn diagram. Any lingering thoughts about the firsts of the universe?
No.
Okay.
Very interesting. Hopefully I'm visualizing it correctly. It feels like a great project for like a fun short film, and maybe someone's probably done it at some point, but just like the little tiny grapefruit size thing, and just like I don't know how difficult it would be to kind of scale that timeline down, or it would have to be like you have to slow down one part and speed up the other in order to kind of like make it match like like however long 15-minute like The Expansion. Like that'd be a cool thing to see, like if there was a way to visualize it anyway, really in like an artistic
Just The Expansion
way. No, like from Bang through inflation and that until Stars. Probably I think Stars is a good like we're here, kind of in familiar territory.
yeah, like where the story goes from here.
Yeah. So it'd be cool just like to see it really, really tiny. Like an old Pixar short or something, like the old Pixar shorts they used to do. I don't know if they're still, that way, but that's my main lingering thought, is that it'd be a cool. I'm imagining obviously my glitter, my black glitter soup, and it like just expanding of just like a wobbling mass of space in theory in art.
I think there is a video. Well, I know there are many videos of like the first 3 minutes that people have tried to animate. So maybe I will try and put one in the research notes for patrons.
Yes.
Yay. Okay, cool. Well, that's all we had. Any sign off, bestie?
It's the beginning of the year. And no matter what you plan to do with the rest of 2026, remember, you are space.
Hell yeah.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram, or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod, or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.